All right, hey everyone. This is a re-recording of the week 4 C++ and practical programming sessions. We're going to be talking about Catkin workspaces, ROS in C++, and message files today. This is unfortunately not the same recording that was watched in regular meetings because we forgot to hit record, so that's our bad. So I'm re-recording it. Originally, Matthew presented this, but I'm going to give it a go. So first of all, we're going to talk about the idea of ROS packages. And ROS packages are just directories that contain sort of files that fit into a specific purpose. So they're grouped in a thematic way, right? For example, there's the geometry messages package in ROS, right? And that contains a bunch of message types, right? For points, quaternions, poses, and a bunch of other different geometry-related data types. And packages can contain message files like that. They can contain functionality. So, for example, you could have a package that contains your motion planning code, right? And in general, when you write code for a ROS robot, right, you're going to be writing packages. You're going to be creating packages and then writing code in those packages. Just a couple of logistical items here. ROS packages are going to require package.xml and cmakelist.txt, right? And those are two files that the first one describes the contents of the package, and the second one describes how to build the package. It's just sort of a regular CMake file like you've been using so far, but with some extra new information that you need or new directives that you give CMake for how to build things and install them in ROS. ROS packages also contain a couple of different directories, so you don't necessarily have to put your files here, but the convention is that you'll have a directory called source, src, for all of your source code, and a directory called message, or msg, for all of your ROS message types. In ROS, we use this tool called Catkin, which is a tool that essentially allows us to build multiple packages. So if you look at something like CMake, which is what you've been using so far, it works on the per package level. It builds a single package. Catkin is what allows us to build lots of packages all at once. It also takes care of if you have, for example, one package that depends on another package. Let's say your motion planner requires the messages from geometry. It will allow you to make sure that they're built and installed in the correct order. Catkin will require something called a workspace, which is a few different things. It's got some directories like this, right? Build, devel, and source. Source is where all of your packages go, all of the source code for your packages. Note that some packages might be pre-installed on your system. That's sort of the ROS distribution, and that's just a lot of packages involving, you know, the basics of ROS that you need for any ROS application, as well as a lot of very common things like geometry messages. But any packages that you write yourself will go in source. Build is the same as the build folder that you usually make with CMake, right? When you do make-dir build and cd build and cmake ... right? It's the same purpose. It's just where all of your compiled object files go. And then devel is basically where some files are generated that allow you to actually, or that you use while you're actually developing the packages, right? So to make a workspace, you just have to follow the following steps. I believe we've got some information on this in the description of each of our exercises, but we'll go through this again just for your sake. So you want to make a workspace directory. A lot of the time, if you don't have something particular you want to call it, you'll just call it catkin workspace, or catkin ws for short. You'll add a source directory. You'll put all of your packages into the source directory in separate folders, and then you'll call catkin make anywhere or while you're in the top level of catkin workspace. And then in general, every time you change code, you're going to want to recompile with catkin make. Catkin make handles both the cmake generation step, so that's the cmake command that you've been running, as well as the actual building command, which is the make command. So it handles both steps all at once. To create a new package, you can use this catkin create package command, which helps you, that should be helpful for avoiding the process of like manually having to generate a package.txt in a CMake lists for a new ROS package. So so far you've learned a lot about how you might write a node or how you might work with nodes, right? Once you already have nodes written, you've learned how to use RQT to visualize them. You've learned how to run them. You've learned how to sort of figure out a bunch of things about how nodes and the topics that they create and publish on are actually operating. However, you haven't actually learned anything about how to make your own node. And in general, you need this, right? Obviously, you're going to be wanting to write your own code. You're not just going to want to use the packages that Ross already has created. So this is an example of a very simple node. All this node is doing is it is essentially it's listening on a particular topic, right? And then it's listening for a point, so an XY tuple on a particular topic, or sorry, an XYZ triple. And it is then calculating the magnitude of that vector, right? So just using the Pythagorean theorem, and it's publishing that magnitude, right? And you can sort of see where some of the points in here are, but let's break it down more specifically. So the first thing that you'll notice is that it does include a bunch of headers. Ross.h is the basic Ross functionality. So whenever you write anything using Ross, you're probably going to need to include Ross.h. Geometry messages / point.h, that's the message for a particular message type. And in this case, it is the 3D point message. Float32 is a message for just a single floating point number, so just a single float variable, basically. And then math.h is just that's just a standard C++ header file that you can use when you want things like square root. So if we look at our main function and sort of walk through the functionality that we get here, the first thing that we do, and in general in any Ross program, of note, each node, you'll note that this program only has one node in it. In Ross 1, each program usually is a node, right? Or each node is its own program, that's their equivalent, and you'll have a bunch of different programs, each with their own main function, one for each of the nodes that you write. In Ross 2, there's a little bit more complex of a story, so if you're on RoboCup, you'll learn a little bit more about how that works, but in Ross 1, that is the case. And then you can see that the first step of this main function, because this is the main function for this node, the first step is just to call Ross init. And this initializes everything related to Ross. In general, it takes these command line arguments, argc and argv. We haven't talked too much about what those do, so don't worry about it. But it also takes this node name, right? And that's the name of the node that you're currently creating. So in this case, we probably shouldn't have called it node name. We probably should have called it something closer to, I don't know, magnitude calculator node or something. I don't know. This is a little bit of a contrived example, but we can then create a private node handle, and this node handle, it gives us a way to create publishers and subscribers, right? So you'll note that we've got a string that we're passing to the constructor of this, right? And that string takes in the namespace of the node, right? And for most cases, you're just going to want to make it a private namespace, although there's a lot of other information. You can, I think last week's video had a longer explanation of what the node namespaces mean. In general, tilde means private, which just means that like it's its own namespace for this node specifically. And then finally, we create a subscriber and a publisher, right? So you'll notice that we've got subscribe and advertise here, right? Those are two functions. Advertise is pretty simple. It's just advertising that we have a particular, or that we will publish a particular particular topic, and we give it in angle brackets that that might be similar syntax to when you create a vector. That might look familiar. Essentially, that's just a list of like types. So in this case, this means the type of the message that we're advertising. And we are creating, or this node is going to publish, a float topic, right? So it's going to publish messages of float type. And we're calling that magnitude topic. And then also creating we're giving it a queue size. In general, this queue size is the number of messages that will be retained. You don't have to worry about it too much for the basics of Ross. For now, just know that it exists. Larger is, in theory, better in that you're not going to drop as many messages, but in general, for things that will be If you're going to process this very quickly, 1 is fine. But going back to the idea of this subscriber, which is a little bit more complicated. So this creates a subscriber, right? And it just does this with the pnh.subscribe, very similar to the pnh.advertise. And it passes, again, this queue size and this topic name. But now we have this callback, right? And what this is saying is that anytime we actually hit this subscriber, right? Anytime that a new message is published to this topic, we're going to call this function point callback, right? And that function is going to, in this case, it's just going to, not return anything, but it's going to compute the value of the magnitude, and it's going to publish that to the float message type, right? Or to this magnitude publisher. So that's all in general. Like, that's a fairly common pattern, right? You'll often have something that handles a new message by publishing something else. It does some calculations on that message and publishes the results on a new topic. And then finally, there's just this while Ross OK, Ross spin once loop. All this does is just forever spins. Spinning is a term for just, check it. Spinning once is checking if there's anything that it can do, so checking if there are any new messages. And then if there are, handle those messages, run the callbacks, right? And it just does this until Ross OK no longer returns true. Ross OK will return false when the node is supposed to die. So this is relatively self-explanatory, I guess, in that case, right? You're just going to run Ross spin once, keep spinning. The node is no longer supposed to be running until you kill it for some reason. Now let's look at the callback that we made, right? Because we did provide this point callback in our subscription, or in our definition of our subscription when we actually created that variable. So let's look at what it actually does. All we're doing is we are taking in a point, right? It doesn't actually return anything. We just take in a point message, and then we do this calculation. We calculate this value mag. We set the value of this float message to mag, and then we publish that float message to the magnitude publisher, right, that we've got above. So note that in when you have a message, they're just like C++ structs, right, where you can access a variable that's in a message by doing message.variable, right? So in this case, that is just float message.value, and we set that to mag. And we publish it using the publisher. So let's talk a little bit about what these message files actually do, right? Or how we define messages, right? Because so far we've seen 2 types of messages. We've seen float32 and we've seen point, right? But there are many other different types of messages that come built into ROS, and also just messages that we might want to make on our own that aren't built into ROS that we find useful. So a message type is created using a message file, which is it's just a file that's got a .msg extension. You'll learn a little bit more about this in an exercise this week. And the file is just a list of all of the data the message will have. So that's basically just a list of variables, right? We've got a couple examples of messages to the right. So this one is actually just pulled from geometry message packages, or from the geometry messages package. And it is a point stamped, which just means a point with an associated timestamp, frame of reference, and sequence number, which is just the first message that you send is 0, the second message is 1, and so on, and so on, and so on. So this point stamp just consists of that information, which is grouped in this header struct, and then a point. And you might use this if you wanted to say, okay, I'm publishing this goal point, right? We want the robot to get to this certain XY position or XYZ position, right? And we want to do that, and I'm sending that message out at time now, right? And that message is published in this particular frame. There are lots of examples of stamped messages, and we've got a little bit more information on those later. So here, this earlier one, right? This velocity pair that I've got circled right now, that's an example of something that we made ourselves, right? And that is that is just a pair of float variables, right, for the left and right velocities of a drivetrain. So you might have for IGBC, right, because you've got those independent left and right wheels, you might have different velocity targets for each of those. And then finally, we've got another example of just another message type that is very important, which is the path, right? And a path is just a sequence of poses. So this is defined in the nav messages package, right? And it just contains a sort of an array, right? This is how you define an array in ROS messages. And it's just an array of geometry message / pose stamped, right? Which is a pose with an associated time. Yeah. Okay. So let's go over this in a little bit more detail. So we saw these headers, right, that were very important in a lot of the messages that we just looked at. In general, the convention is that any message that has a header is going to be called stamped. So like we've got point stamped here, right, or path, which isn't necessarily stamped, but we just sort of assume that like all paths have a stamp associated with them. And these contain sequence ID, timestamp, and frame ID. So sequence ID is just an incrementing count. It just goes up each message. Timestamp is basically just it's just the current time when you send the message. And frame ID is a string representing which frame of reference you're in. That may or may not be important for you depending on which team you're in. I think that RoboNav and Robo Racing use that a lot. RoboCup doesn't really have a lot of frames of reference or a lot of different frames of reference to manage, so we don't really use that. But this would be like, for example, if you had this in the camera frame, right, you might have a string called camera. All right, so we've got a couple of exercises planned for you this week. The first one is going to be just adding a subscriber to a node that is pretty much written for you, except for that subscriber, right? Then we're going to be using RQT and looking at how nodes actually operate, right? And a node that we write operates. And then the last one is going to be writing a custom message type. And we've got those all published, and I will send out the link with the same email that contains this recording. All right, so that's all for this lesson. Have a good week, and good luck with the exercises.